Hey, welcome back, geometry students. You know, we're down to the home stretch, aren't we? We just have just a few days left of e-learning this year. We are going to stick in the last few topics here in Unit 12, and we're going to be studying some topics involving circles for the last 4 or 5 days here, guys. Today, the topic is we'll introduce you to what a tangent of a circle is and some of the properties that go along with it. So I encourage you to follow along as we look at 3 or 4 important theorems about tangents, and you'll be applying them in your homework assignment in MathXL today, okay? Your objective here is just that. You're going to use the properties of tangents drawn to a circle. Well, what is a tangent to a circle? Let's introduce that. Let's introduce that first. So a tangent is a line drawn outside of a circle, touching it at just one point. Okay, so here we have a circle and a point B. Point B is on the circle, and then there's a point A that is outside the circle. And then line AB comes in, and the line, it's important the line touches the circle only at the one point. If the line crosses through multiple points, such as the one I'm going to draw now, okay, that is different. That's not a tangent. We'll cover that situation in a later lesson, probably in a couple of days from now. So it's important that you know that a tangent will only touch the circle at the one point, and that is then called the point of tangency. Okay? And a tangent can be a line, as I have here, that extends both directions indefinitely. A tangent could also be a ray. Maybe it only starts at B and goes out toward A, and we don't even see the other rest of it. Okay. Or a tangent could be a segment. We can just draw no arrows on this, just start and stop. Okay, so the main thing here is you just understand what a tangent looks like and what it doesn't look like. And we're going to introduce you to about 3 special properties of tangents today in our lesson. So the first one is what is it that happens when a tangent is drawn, such as what we have here. The point of tangency is point P. Okay, so let's just mark that nice and dark for us here. And now I'm going to connect point P to the center of the circle and make a radius. Okay, so the theorem or the relationship that we have here is, let's read it. It says if a line, like line AB, is tangent to a circle and it's touching at point P here, it is perpendicular, the line is perpendicular to the radius. I want you to think about that. Remember what that word perpendicular means, and notice then that what that means is we can take this diagram right here and add in the right angle symbol right there at point P. So line AB and then the radius O to P, they're making a right angle. Okay, so what we're going to do is let's try and use that property now to solve a problem involving a circle, some tangents, and some angles that we form when I connect them all here. It says ML, segment ML, which is the one I'm pointing to right now, segment MN, they are both tangents to circle O. O is the center point. What is the value of X? Now, X is the angle at point M. So X represents the angle measurement that I'm putting in right there. So two pieces of past learning that'll help here. First one is just what we just talked about a minute ago, that anytime we have a circle and we have a tangent, in this case a tangent segment, the radius that connects to the point of tangency is perpendicular to that tangent. So we can put a right angle right there at L, and in the very same way we can put a right angle here at N. Okay. The other piece of past learning that you're going to want to draw on is that there is a quadrilateral, a 4-sided shape. If I were to trace all the way around from O to N to M to L and back to O, that's a quadrilateral. So 4 sides. And we learned in a prior unit about the relationship between the total number of degrees in a polygon and how that relates to the number of sides. I encourage you to think back for a little bit and see if you remember that, or just pause the video and think to yourself for a minute. So the relationship we're looking for is that, remember, if you take the number of sides, subtract 2, and then you multiply by that by 180, you get the number of degrees. So I took 4 minus 2 times 180, that's 2 times 180, or 360 degrees total. Okay, now in my quadrilateral, I already know 3 of the angles. I know angle L is 90, I know angle N is 90, and angle LON is 117. So all I've got to do is now find angle X. So the first thing I'm going to do is add up the 3 angles I do know. So I'm going to add up 90, 90, and 117. Now you can do that with the calculator or just by hand, like I'm going to do here. 7, 9, 9 is 18. This is going to be 19. And this is going to be 297 degrees among the 3 angles that I do know. So what's left for me to do is subtract that from the 360 that's in the entire polygon. And so a quick bit of math here, and this is going to be 63 degrees, and that makes answer choice B. Okay, well, let's try another one kind of like that, and this time I actually encourage you to pause the video and try this one yourself first. Okay, so if you try it yourself, hopefully what you notice first is, again, a tangent segment and then a radius, or in this case actually a diameter, which makes a right angle right there at point D. And this time we have a triangle, so there are 3 angles in a triangle, and that makes 180 degrees total. But 2 of the angles are already known. We have a 90 and a 38. So let's add that together first and get 128. And now all I've got to do is subtract that. Do that quick, or you can use a calculator. And I'm getting 52 degrees this time. Okay, now you might also just write an equation here. I could have written something like x plus 90 plus 38 equals 180, and just think of it as an equation. I'm solving for x. Well, that would be like doing x plus 128 equals 180, and then I'm just going to solve by subtracting 128 from 180, and you get 52. Okay. Okay, well, our second property is this one. Now, this is just really the reverse or converse of the way we said it a minute ago, which means the ifs and the thens of the previous theorem are just reversed, right? So this one says if you have a line in a plane, in the same plane as a circle, and if it is perpendicular to the radius of a circle, so it's going to touch the point on the circle and it makes a right angle, then you can say that this is a tangent line. Okay, so just to summarize there, the first theorem said if you have a tangent line that is touching a radius, they are perpendicular. Then they are perpendicular. This is the converse, and that is if a line touches a radius and they make a right angle, then that line is a tangent line. So we're going to now test our understanding of that theorem in a couple of example problems. So problem 4 here says, is line ML, segment ML, which is the one marked right here, that's unit 24 units, is that a tangent to circle N? Remember the theorem, it says if the line makes a right angle to a radius. So what we're trying to do here is test it out, basically saying, is angle L a right angle. Okay? So we could expand that even further and take a look at the triangle we have from M to N to L. We could basically saying, is this a right triangle? So is triangle NLM a right? That's another question that could be asked that would answer the original question. Okay, now this we have actually done before, determining if a triangle is a right triangle. If the triangle is a right triangle, its sides will follow the Pythagorean theorem. And so in this triangle, the candidate for the hypotenuse is the NM side 25. Okay, so what we're going to check here is 7 squared plus 24 squared equal to 25 squared. And we're going to check that math now and find out. Okay, so we clear our calculator and we're just going to check the left side first by checking what is 7 squared plus 24 squared. That can all be done by the calculator. That's 625. Okay, let's check and see what 25 squared is. 25 squared. How about that? 625 also. Okay, so because these two sides squared and added together make 25 squared, the answer to the question is yes. There is a right angle right there, and that means that ML is perpendicular to M or LN, and that makes ML a tangent. Okay. So we'll try this one more time. Now the sides this time are 4, 7, and 8. We're trying to determine basically if this is a right angle right here. Okay? Because in order for ML to be a tangent, it must make a right angle to the radius NL. I encourage you to just pause for a minute and see if you can write the equation we're going to try and check out. Okay, so in this problem, the candidate for the hypotenuse is NM, or 8. So we're going to check if 4 squared plus 7 squared equals 8 squared. Okay, question mark. Now, 4 squared is 4 times 4. 7 squared is 7 times 7. And 8 squared is 64. We might not even need a calculator this time. If you try and add 16 and 49, you actually get 65, not 64. So this time the answer is no. This is not, ML is not a tangent to the circle at all. Whoops. Now one last property today, and that is to take the situation where maybe we draw two tangents to the same circle, and those two tangents then intersect at a point outside the circle, like point B here. So the theorem says if two tangents share a common endpoint, meaning they intersect at a point outside the circle, then those two tangent segments are congruent. I've already gone ahead and marked the congruent marks here. So A to B is congruent to AC because they are both tangents to the same circle and they have a common point B. Okay, so you're going to use that property here to determine the perimeter of this triangle. Now, the triangle is made up of three tangents. Now, one way they describe that here is it says circle O is inscribed in triangle ABC. And the word inscribed means it touches but doesn't cross out of the triangle. Okay, so it is tangent to the triangle's three sides, just like this. And so now you are given three segments of this triangle, but there's also a couple missing here. So what we're going to notice is from A to B, or A to D to B, is all one tangent. Okay, so is A to F to C all a tangent to the circle, and so is from C to E to B. So the theorem on our last page says, take point A for example. If A to D is a tangent segment and A to F is a tangent segment, I can put congruent marks there. Now if A to D is 10, I can put another 10 right there. Same thing on these other two sides. So if from B to D is 15, I can put 15 again from B to E. And likewise, if C to F is 8, I can put another 8 right there. C to E will be 8. So now all I've got to do to get the perimeter is to add up all the sides. Now let's just go ahead and add them up or subtotal them as we go here. So from A to B would be 10 and 15 or 25. From A to C would be 10 and 8, so that would be 18. And from B to C is 15 and 8, which is going to be 23. Okay, so we've got to do 25 plus 23 plus 18. And so let's see, 25, 20, let's just go ahead and grab the calculator for that. So 25 plus 23 plus 18 gives me a grand total of 66. That's the perimeter. Okay, well, you'll be doing problems like this in MathXL today. I wish you the best, and let me know if you have any problems or questions. And please, if you have any makeup work to do, or if you're getting behind, please do your best to get caught up in your missing assignments, guys. We only have a couple weeks to go. Let's all do our best. We'll see you here in a couple days.